Okay, welcome back, lads and ladies. This, of course, is MAC2312 Calculus 2. And today we are going to talk about integration by parts, which is one of these really exciting lectures. There's a handful of lectures throughout the semester where it's like, whoa, we're doing something big. This is like a big step forwards. And today we have probably our single biggest step forwards with respect to integration techniques. So today is where you go from being amateur integrators to expert integrators, because the method we're learning today, although in one sense it's a very simple kind of fundamental method akin to learning the product rule for derivatives, on the other hand is one of the more powerful techniques that exists in the entirety of calculus. So I'm very excited to share it with you, and let's get to it. Get this thing focused. Okay, so MAC 2312, section 004, which is Calc 2, the date, it's January 21st, 2022. And today, with all the enthusiasm we can muster, we're talking about integration by parts, which is section 7.1. This section marks our transition into kind of the serious part of the class, right? So 5.5 through 6.4 is kind of warm-up stuff. The actual calculus that we've been doing is all stuff that you learned back in Calc 1, right? I mean, sure, we've learned how to do lots of new stuff with them. Finding volumes and calculating work and all of that stuff is new. But the integrals you write down for each of those problems were integrals you could have done in Calc 1. And you split them up, power rule, U sub, that sort of thing. Today, I will show you how to do calculus that you could not do yesterday, which is, I think, very exciting. Before I go further, I just wanted to remind you guys, if it is possible, I would really appreciate it if you leave your cameras on. I understand that it feels like a bit of an inconvenience, but my ability to see your face tells me so much about how well the material is clicking, and it will really help me pace the lecture in a way that is maximally effective for you. So that's all I wanted to say. If you can turn your camera on, I would really appreciate that. That makes it feel a little bit more like a classroom and helps me deliver the lecture in a way that is more effective. So if you can, please turn it on. Thank you very much, Matthew, Elijah, Maria. I appreciate that. Thank you, guys. Okay, so integration by parts. Like I said, it's a backwards product rule. It's a product rule for integration. That's true. Arthur Mattock, who is the head of the differential equations research group at the Massachusetts Institute of Technology, MIT, once said that integration by parts is the most powerful theoretical method known to man. And a student of mine, or a former student of mine, is publishing a paper this year in the College of, what is it? Journal of College Mathematics, a peer-reviewed scholarly paper, where he uses integration by parts to come up with some really cool formulas for integrals of the gamma function and things like that. So just to give you an idea of how heavy this is, it's not very hard to use, but you'd be amazed what you can do with it. It's like a screwdriver. You can do all sorts of shit with it, even though it's a fairly simple tool. Let me begin just by telling you the result. It's a formula, right? Just like the product rule is a formula, it's a formula. What this says is if u equals u of x and v equals v of x are differentiable functions with differentials du. So remember, just like how you calculate differentials when you're making a substitution, du would be u primed of x dx, and dv is v primed of x dx. So when you see du, just think the derivative of the u function. And when you see dv, just think the derivative of the v function. Then, and there's two separate formulas. I'm going to give you one for indefinite integrals and one for definite integrals. They essentially say the same thing, but we apply them slightly differently. The indefinite integral version says the integral of u dv, so it's like the u function times the derivative of the v function, is equal to u times v minus the integral of v du. This is the way it's normally written. Okay, Mark, yeah, no stress, no stress. So I know this looks a little bit weird, right? It doesn't look like functions right away, but remember that u is a function and dv is like the derivative of v, so it's also a function. So everything here are functions. And the other version for definite integrals says that the integral from a to b of u times dv is u times v evaluated from a to b minus the integral from a to b of v times du. So you see, they're essentially the same thing. It's just that the definite integral version has this evaluation bracket everywhere. Well, that is it. That's integration by parts. There are two proofs that I think are appropriate for our level. One of them is relatively easy to share with you, and the other one, rather than conveying to you here in the notes, I'm going to show you a picture on Stack Exchange that I have linked for you in the modules. But a quick proof of the first guy. Right, so I'll call this 1. I'll call this 2. So a quick proof of 1. Comes from the product rule. What I'm going to do is I'm going to rearrange the integral of u dv equals uv minus the integral of v du with the integrals on the left. So I'm going to add this integral over here. And that will give me integral of u dv plus the integral of v du is equal to u times v. And then my next little step, I'm just going to replace the u's. Like everywhere there's a u, I'm going to write u of x to remind you it's a function of x. Everywhere there's a v, I'm going to write v of x. And I'm going to do the same thing with the differentials, dv and du. I'm going to write dv as v primed of x dx and du as u primed of x dx. So this is the integral of u of x times v primed of x dx. That's the first integral. Plus the integral of v of x times u primed of x dx. That's the second integral. Equals u of x times v of x. Okay. Now, on the left-hand side here, I have two integrals, and they're added up, so I can put them together into one integral. That's really the integral of parentheses u of x times v primed of x plus v of x times u primed of x dx. And it says this is equal to u of x times v of x. And now you see the product rule in here, don't you? What does this bottom line say? it says that the antiderivative of uv prime plus vu prime is u times v. So if I differentiate on both sides with respect to x, if I take d dx of both sides, we get d dx of the integral of u of x times v primed of x plus v of x times u primed of x dx is equal to d dx of u of x times v of x. And then I ask you, what is the derivative of the indefinite integral of some stuff? I'm taking the derivative of the antiderivative of this thing. So the derivative and the integral cancel each other. And we get u of x times v primed of x plus v of x times u primed of x is equal to the derivative d dx of u of x v of x. And wouldn't you know it, that's the product rule. Right? This is the product rule from Calc 1. Right? Section 3.2 in your textbook. The derivative of a product of two functions, u times v, is u prime times v plus u times v prime. And we know that the product rule is a true statement. Right? So my integration by parts formula is logically equivalent to the product rule. That's what these double arrows mean, right? It means logically equivalent to, or is the same as. So integration by parts is true if and only if the product rule is true. And we know the product rule is true. So the integration by parts formula must be true. In other words, you can do this. This is a valid thing to do. Neat, right? Okay, so it's nice to know that the formula we're using is correct, but how do we use it? The obvious answer is kind of like with the product rule, right? If you want to integrate something that you would use the product rule to differentiate, then maybe you should use this to integrate it, right? Because this is the integration version of the product rule. Now, we know that's not always true, right? Like if you want to integrate x times the sine of x squared, that was a problem from your very first homework set. That's a little u sub. But anytime you have a product of two functions that you're trying to integrate, you can attempt to use IVP. And some classics are things that you would definitely think look very product rule-y. So if I wanted to integrate x times e to the x dx, differentiating this would certainly be a product rule derivative, right? So maybe integrating it is a product rule integral, i.e. integration by parts. The way you apply this formula you have to, right, this says that the integral of u times dv is equal to some stuff. So we have to look at our integral here and try to understand this thing as u times dv. So I need to pick one part of this to call u and one part of it to call dv. And the part that I choose to call dv should include the dx because the dv is a differential. Okay. So what we do is we choose one part to be u and the other part to be dv, and that's hence the name integration by parts. I'm going to choose x to be u. Now I'll explain how I make this choice later. But I'm going to choose this piece to be u, and I'm going to choose e to the x dx to be dv. We're not making a substitution. I want to be clear about that. It's a shame that we use the letter u when we talk about substitutions so often, but this is not a substitution. This is something very different. Now my formula says integral of u times dv is equal to uv minus the integral of v du. So in that formula, there is a du, which I'll need to calculate from u, and there is a v, which I'll need to calculate from dv. So we choose these, and then we calculate du and v. So if u is equal to x, what is the differential du? Anybody? Yeah, very good. Just like with your substitutions, the calculation of a differential is the same. So King and Kim and chat are correct. Du here is just dx. The derivative of x is 1. So du dx is 1, which means du is 1 dx, or just dx. To go from dv to v, we integrate, right? So if I integrate e to the x dx, what do I get? There's no need to be shy. You can shout out. Remember, space bar is like a walkie-talkie button. Yeah, e to the x. Thank you, guys. Okay, what I like to do is put all of this in a little box, just like with my u subs, tuck it out of the way so it doesn't clog up the workspace. This is the IBP table. And every time you do an integration by parts problem, you begin by choosing the first row of this table from your integrand, splitting this up, and then calculating the missing pieces, du and v. So every time you do an integration by parts or IBP problem, you're going to make a table like this. And then you just plug into the formula. The formula says the integral of u dv is equal to u times v minus the integral of v du. And a notation pro tip, if you put a little bit of a tail on your u's and you make your v's hard on the bottom, edgy like that, then you'll never confuse one for the other. So the integral of u dv, that's my integral. That's x times dv is e to the x dx. And according to my formula, my integration by parts formula, this should be equal to u times v, which is x times e to the x outside of the integral, minus the integral of v times du. Now v is e to the x, and du is just dx. So the integral I'm trying to calculate is equal to this stuff. This part is done. We don't have to do anything else with this. This part still has an integral. And what you should ask yourself is this integral easier than the integral I started with? Does anybody have an opinion on this? Which integral would you rather do? The integral of e to the x or the integral of x times e to the x? The x is gone here, right? That's what makes this problem challenging in the first place. So we can finish just by calculating the integral of e to the x. So this is x e to the x minus e to the x, and then we put our plus c on at the end here. And that's it. This is your answer. I want to make a couple little notes. This is as gentle as these problems can possibly get. What I'm about to tell you is going to show up as a question on your first test. Note. The integral of x times e to the x dx, which we just found should be x e to the x minus e to the x plus c, is not x squared over 2 times e to the x plus c. If you have two functions multiplied together, you can't just integrate each of them on their own. This is true of derivatives also, right? If you want to differentiate two functions multiplied together, you don't just differentiate each one and multiply the answers. You have to use the product rule. And the same thing is true of integrals. If you have two functions like x times e to the x multiplied together, to integrate them, you have to use the integral version of the product rule. You cannot just integrate each one on their own. If you differentiate this with the product rule, you will not get x times e to the x. And in general, the integral of f of x times g of x dx is not the integral of f of x dx times the integral of g of x dx. This is why we need integration by parts, right? Because integrals, like derivatives, do not play nice with multiplication. Remember, in Calc 1, you have a product rule, you have a quotient rule, all this stuff for differentiating products of functions and quotients of functions. The integral operator is just like a backwards derivative. So if that shit didn't work for derivatives, it's not going to work for integrals either. And a common mistake very early in Calc 2 is to try to calculate integrals in this fashion, where you say, oh, I know the antiderivative of x, that's x squared over 2. I know the antiderivative of e to the x, that's e to the x. So I'm just going to multiply those. That's not correct. It does not work. This is what works. With that preaching out of the way, are there any questions about the purple stuff? Okay. And if we wanted to check our work, I could differentiate this, right? This piece I would need to differentiate with the product rule. And when I put everything together, you will just get x times e to the x. I'm not going to spend class time doing that. But. That problem is a part of a big family of problems that are all handled the same sort of way. E to the x is a function that when you differentiate it or integrate it, it kind of stays the same. It doesn't change. Sine and cosine are also kind of like that. They go back and forth from sine to cosine, but they never go away. They never change like a lot. If you want to integrate any function like that times any polynomial, right? Like x on its own is a polynomial, x squared or x cubed minus 7x. If you want to integrate anything like that, it goes the same sort of way. So as in the last problem, I have like a polynomial times the sine, cosine, e to the x, one of those functions that are kind of like, they don't change much when you do the calculus operations to them. So we're going to attack it the same way. We're going to do integration by parts, which means we have to start by choosing u and dv. The way we do this is called a partition. You split your integral up into pieces. So it has to be the case that u times dv is the whole integral, and there can't be any overlap between the two. Well, such a separation is called a partition. Now here, I'm going to pick u to be the polynomial piece, again, like we did last time. X squared plus 3x is the polynomial piece this time. And I'm going to pick dv to be everything else. So dv here is cos x dx. And when you choose u and dv, that's generally how it's going to go. You're going to pick one piece to be u, and then everything else will be dv. So once you've chosen u, you don't have to think any further about how to pick dv. I know I'm burying the lead, Maria. I still haven't told you. Yes, there are rules, and I will share them with you in just a second, but I want to kind of lead you to them through this one more example. So I will give you a rule in just a minute. But before I give you the rule, let's go ahead and just trust that this is a good choice for u and dv here. Carry out the problem, and then we'll see if you can kind of smell the rules coming. So if I take the differential of x squared plus 3x, that is 2x plus 3, all in parentheses, times dx. And if I integrate cos x dx to get v, that is just sine of x. So here's my little integration by parts table. And again, writing the IVP here helps your reader to understand what's going on. They can tell, oh, you're doing integration by parts. Okay, I get it. It's not a U sub, it's something else. And then you apply the formula. Now, I'm not going to write the formula out this time. I'm just going to write down what you get from it. What I will do is I'll label this here as U and dv. So the integral of u times dv is equal to u times v. So I'll put that down here. U is x squared plus 3x times v is sine of x. And then you get minus the integral of v times du. Okay, uv minus the integral of v du. Like I said last time, what you should do is look at this integral and ask, is this better than the integral I started with? Is this easier than this? They're quite similar. But what's happened is that the degree of the polynomial piece, which was originally 2, right? This was originally a quadratic polynomial, has gone down. This is now a degree 1 or linear polynomial. And if I could get rid of that polynomial all the way, then I just have a sine or a cosine. I know how to integrate those. So if I can knock this from a quadratic function down to a linear function with one run of integration by parts, what could I do to get rid of this completely? Yeah, exactly, Matthew. More integration by parts. Tyler, thank you. Yeah, if I do the same sort of thing again, where I pick this to be u, pick the polynomial piece to be u, and pick dv to be everything else, then when I go from u to du, the polynomial piece here, 2x plus 3, will go from a linear function down to a constant function. And that's very nice. So we're going to do IBP again. And I will pick u and dv in the same fashion. U is going to be the polynomial piece, 2x plus 3 this time. And dv will be everything else, which is sine of x dx. And then I calculate du from u. If u is 2x plus 3, then du is 2 dx. The derivative of 2x plus 3 is just 2. And if I integrate sine of x, I get negative cos of x. So here's my second little integration by parts table. The chunk that's out front from my first integration by parts, this piece is done, but I need to keep writing it. It's a part of my answer. It doesn't go away. I just don't do anything with it in this step. So I still have x squared plus 3x times the sine of x. This negative is still here. And I'm going to replace now this integral by what integration by parts 2 says it is equal to. But this negative needs to distribute over everything. So when you do this, open up a big parentheses. We're going to replace this integral by a difference of two pieces here, according to the integration by parts formula. And that whole thing is being subtracted. So we need this parentheses to tell us to distribute the negative through. This little integral is equal to his u times his v. That's 2x plus 3 times negative cosine of x minus the integral of this v times this du, which is negative cosine of x times 2 dx. And then I close my big parentheses. One of the dangers in integration by parts, because there is a negative in the formula, and you can encounter negatives within your table, is that you can get lots and lots and lots and lots of negative signs piling up. And one of the most common mistakes on these problems is to like forget these parentheses, forget to distribute, that sort of thing. So be very careful with your SIGN signs, your plus and minus signs. We're almost done. If you look at this integral here, this is actually not hard, right? This is just the integral of cosine after you pop out all the constants. But before we do that, we should clean everything up. We're going to distribute the negatives. So I have x squared plus 3x times the sine of x. Distributing this negative here, this piece would be like 2x plus 3 times negative cos x, or negative 2x plus 3 cos x. That will become positive 2x plus 3 cos x. This minus and this minus would make these positive. And then when I distribute this minus from the front here, you'll have 1, 2, 3 negatives altogether. We'll make that minus, and then I'll pop out the 2 times the integral of cosine x dx, like this. And now we're just about done. The integral of cosine, that is easy, right? Whose derivative is cosine? That's just sine. So this becomes x squared plus 3x times the sine of x plus 2x plus 3 times the cosine of x minus 2 times the sine of x plus a constant. And that's job done. I want to pause for a second, give you guys time to get this in your notes nice and clean. Make sure, check all your minus signs are in the right place and you've got parentheses where you need them. Are there any questions about what we did here? The 2 here, if I'm looking at this integral, kind of pretend like I'm just focusing on the highlighted portion. This 2 is a constant multiple, right? Inside this integral, I have -1 times cosine of x times 2 times dx. So I could pop a -2 out front, which would make this plus 2 times the integral of cos x dx. And then when I distribute this additional negative, that plus turns into a minus. But popping the constant out of the integral just makes it easier to see what I have to do with this. Oh, cosine, integral of cosine is sine. So as long as you have a constant multiple, a constant multiplying your function inside the integral, he can always pop out. And that's always a nice thing to do. Of course. Any other questions about how we get to here? Yeah, so a good question coming in the DMs there. Is it the case that with integration by parts problems, we just IBP, IBP, IBP until the polynomial goes away or until you get a constant? If the problem is a polynomial times sine, cosine, or an exponential, then yes. And that's exactly what I wanted to say next. So you're ready to go to the next bit here. In general, to solve integrals of the form integral of a polynomial times a sine function or a cosine function or an exponential, right? And it doesn't have to be exactly sine of x. It could be sine of pi x, or it could be cosine of 2x, or e to the negative x. Any sine, cosine, or exponential times a polynomial, we run IBP until IBP with u equal to the polynomial piece until the polynomial is constant. Each time you run integration by parts with u equal to the polynomial piece, you will differentiate the polynomial piece one time. So if you have a degree 2 polynomial at the start, you'll have to run integration by parts twice. Because you differentiate a quadratic twice, it becomes constant. If you have a degree 3 polynomial here, you'll have to run integration by parts 3 times. So like x cubed times e to the x, that's 3 runs of IBP. X to the 4 times e to the x, that's 4 runs of IBP. Those can get, right, it's a good chunk of writing here. And there is a method for solving these problems a little bit more quickly called tabular integration by parts. And what that does, it just allows you to set up all the IBP tables at once. It's not something we teach here officially at Santa Fe, but if you want to, you of course are free to look at things like this. I'm sending in the chat. Oh, it's a Google link. It's nasty. Here, better link, second one, same thing. You see there he's doing the integral of x to the 4 times sine of x. If the polynomial is a large degree polynomial, then the tabular method is the way to go for sure, because writing all these steps out separately takes so long. So yes, if your integral looks like this, then you run integration by parts, differentiating the polynomial each time until it's gone. But there are many integrals that we want to do which require integration by parts that don't look like this. So these are kind of the easiest ones to wrap our head around, because they're the sort of thing where, okay, you differentiate one piece, you integrate the other piece, and differentiating that first piece makes things nicer every time. This is where I need to share with you the more general rule for picking u and dv. Intuitively, we should choose for u something that gets nicer if you differentiate it. And for dv, something that gets nicer if we integrate it. In fact, that guy, Arthur Matic, that I referenced at the very start of the lecture, the MIT professor, head of the differential equation stuff there, the way he teaches integration by parts is just to say, you know, pick a piece to differentiate, pick a piece to integrate, and then he has a little mnemonic. He says, do the integral, don't do the derivative, then subtract the integral of what you get when you do both. I think that's a little confusing, but this sort of general ethos behind picking u and dv is a good one. When I learned integration by parts, this is what I was told, right? Pick for you something you want to differentiate. And what do I mean by nicer? I mean, gets easier to integrate, right? So something whose derivative is less vexing to integrate. So like the natural log is a good example of this, right? ln of x is not something we know how to integrate right now. Right? It's not 1 over x, that's the derivative. The derivative of the natural log is 1 over x, and that's easy to integrate. We know how to do that. So when you differentiate the natural log, it gets nicer. The same thing is true of the inverse tangent function, right? Arctan of x. Arctan of x is a scary inverse trig function, but its derivative is 1 over 1 plus x squared. That's not so scary. That's a rational function. That's another example of a function that gets nicer when you differentiate it. So those are the sort of things you want to choose for u. Logarithms, inverse trig functions, polynomials. For dv, right, because we have to partition the integrand, dv will always just be everything else. So the second part of this sentence really isn't all that important. Once you've chosen u, dv is determined. It's everything else. And there is a strict guideline for this that most professors teach, and I will share it with you. Some people use slightly different letters. What this is a hierarchy of things you want to choose for you. We call it the Lipet rule. L here stands for logarithms. If your integral has any logarithms in it, then you should choose those to be u and everything else to be dv. If your integral doesn't have any logarithms in it, you're going to look for inverse functions like arctangent. If there are not any logarithms, but there are inverse functions in your integral, then you should pick those to be u and everything else to be dv. P here stands for polynomial. If there are no logs and there are no inverse functions, but there is a polynomial, then that's what you should choose for u. E stands for exponential. T stands for trig. So again, it's a hierarchy. You start at the top. If an item starting at the top appears in your integral, choose that for u and everything else for dv. Right? So you just look at your integral and you move down this list. The first time you see one of these things in your integral, you stop, you make that u and everything else dv, and you run your integration by parts. This is the most common procedure for teaching how to pick u and dv. Okay. If an item, the parenthetical here is starting at top. So starting up here with logarithms and moving down. If an item starting at the top appears in your integrand, choose that for u and everything else for dv. This is slightly out of focus, isn't it? Yeah, there we go. Any other questions on this, on just the rule? Okay, let's try another example then. I mentioned we don't know how to integrate the natural log function. I'm going to start with something a little bit more vexing. All right. So I want to integrate x times the natural log of x. This looks product rule-y, right? It looks like something you would differentiate with the product rule. So integration by parts, good idea. What should I pick for u and what should I pick for dv? So we want to follow our LIPET rule here. We could try running this with u equal to x and dv equal to ln of x dx, but we're going to run into trouble right away because to integrate dv, it would require knowing the antiderivative of ln x, which we do not know. I'd like to see a few more answers. People are DMing me answers. That's fine. DMs are great. Don't be shy about shouting out or posting in public chat or DMs. I'd like to see just a few more ideas here. What should I pick for u and dv? I promise I won't make fun of you or anything if you're wrong. But just follow the rule. What does the rule say I should pick? Good. Yeah, very good. All right. So I look at my rule here and it says if there are any logarithms, I should pick that for u, right? That's the first thing on the list. So it's the first thing I look for here. Are there any logarithms? Yeah, this ln of x. This shows up before polynomials. X is a polynomial. So if there were not any logarithms or inverse functions, then I would pick x to be u. But right in my first step here, logarithms, I do run into a log. So that's what I should pick for u. What I'm going to do. So I'm going to do integration by parts, and I'm going to pick this to be my function u. So what is dv going to be? Very good, Amanda. Yeah, dv is always just everything else. And everything else here is x times dx. So once you've chosen u, following your LIPET rule, dv is just all the other stuff that's there. Now we complete our IBP table by calculating du from u and v from dv. The derivative of ln x is 1 over x. So du is 1 over x dx. And again, please don't forget to write the differentials here. I will take points off for that on the test. If dv is x dx, then v is the antiderivative for x squared over 2. And another neat trick, you could actually use any antiderivative here, right? You notice I'm not writing a plus c. Usually when we do an integral, we write a plus c, right? I could pick x squared over 2 plus 3, or x squared over 2 minus 7. And sometimes that is helpful. But the standard way to do it is just to leave off the constant. Okay. So there's the IBP table I get from choosing u according to my LIPET rule as the logarithm, dv as everything else, and then just filling out the rest of the stuff. Then according to my integration by parts formula, this integral, which is the integral of u times dv, should be u times v, which is the natural log of x times x squared over 2. Another notation tip, always put the inside of your logs in parentheses, right? Without the parentheses here, it's not clear if the x squared over 2 is inside or outside. Minus the integral of v du. Okay, well, v is x squared over 2 times du is 1 over x dx. And again, we should ask ourselves, have things gotten better? Is this integral easier than the integral I started with? I say yes, because this simplifies beautifully. X squared over 2 times 1 over x. You can cancel this x with one of the x's up here, right? This is x times x upstairs, and this is an x downstairs. And then this 2 downstairs is a factor of 1/2 that can come out of the integral. So this becomes natural log of x times x squared over 2 minus 1/2 integral of x dx. All right, where these are equal to each other, just simplifying and applying the rules for integrals. All right, I haven't done any integration there. I just canceled the x's and I popped out the 1/2. And we're almost done. This is sure as shit. This is an easier integral than the integral I started with, right? Things have indeed gotten better. And that's the little check you should run in your brain. Is this better than what I started with? Yes. Okay, keep going then. If the answer to that question is no, you need to stop and try something else here. But the answer is definitely a yes. I would way rather integrate x than x ln x. So I get this piece still chilling. Minus 1/2 times antiderivative for x is again x squared over 2. And now I write my plus c because there is no more integral. And that's it, you're done. Of course, 1/2 times x squared over 2 is x squared over 4. You could combine those if you want. You do have an x squared here and an x squared here. You could factor that out if you want. The only thing that I would do is to combine and maybe write the x squareds in front. X squared over 2 times the natural log of x minus x squared over 4 plus a constant. When you have a logarithm times a power or something like that, I think it's always nice to put the power function out front, because then it's really clear that this is not inside the log. Here it's maybe a little unclear. Here it's 100% clear. Okay, any questions on what we did here or how that rule guided us to this choice of u and dv? Okay. I have a question that I've just launched in a poll. Is the integral of the natural log of x 1 over x? True or false? Now, this is going to stay anonymous. I'll tell you, this is also a question that routinely shows up on my first exam. Yeah, so we're pretty evenly split here, 35%, 65%, 65% say false, and that's the correct answer. So the correct answer here is false. The integral of 1 over x is ln of x, but the integral of ln of x is not 1 over x. So at this stage, do we know the integral of ln x? The answer is not yet, not yet. What we do know that the integral of 1 over x dx is ln of x plus c. And we know that because in Calc 1, you learned that the derivative of ln of x is 1 over x. But an antiderivative for ln x is never discussed in Calc 1. And there's a reason for that, because it requires integration by parts. So don't confuse this statement with the statement that integral ln x is 1 over x. They say very different things, right? The integral of a function is not the same as the derivative of that function. It's the backwards derivative of that function. So this is true, and this is true, but the question from the poll is false. So that's our next example. Let's do it. I think in some ways this is easier than the one we did before, but in some ways it's a little bit trickier because it's not entirely clear what dv is going to be, especially if you're a little sloppy with your notation and you have a tendency to leave off the dx's. So this problem is a good example of why you should always write your differentials. There is no substitution which will save us here. And this is not one of the integrals that you learn, one of the rules that you learn in Calc 1. But if you keep your Lipet rule handy, you know that anytime you see an integral with a logarithm in it, you should be thinking maybe integration by parts. Well, what does that leave for dv? If I pick u to be ln of x following my Lipet rule, what is dv? Yeah, okay, I like the corrected answer there. Thank you, Fabrice. Yeah, dv is going to be 1 dx, or just dx, right? If you pick this piece to be u, then everything else has to be dv. Well, the only thing that's left is dx. And that's how you integrate the natural log function. You set up your integration by parts like this. And then your du is 1 over x dx. We do know the derivative of ln x. And your v, the integral of dx, is just x. On both this one and the last one, I remember learning it thinking this felt a little weird. This felt like going backwards because I'm introducing powers of x, right? On this one, I went from something that didn't have any x's in it to something that is going to have some x's. And on the last one, I went from something that had an x to something that had an x squared. It kind of feels like you're going the wrong way. But the more important thing is getting rid of the logarithm. The logarithm makes the integral hard. So getting rid of that, turning that into a 1 over x by differentiating it, is the move. So now, according to my by parts formula, this should be u times v, ln of x times x, minus the integral of v du, and that is x times 1 over x dx. And you see how nice that integral is, even nicer than the last one. X times 1 over x, like 2 times 1/2, or pi times 1 over pi, is just 1. Again, I like to write the x's in front of the logarithms here, so I'm going to write x ln x. And then you have here just minus the integral of 1 dx, or minus the integral of dx. The integral of dx on a good day is x. So this is x times the natural log of x minus x plus c. And this is the one problem I am going to check by hand by taking a derivative. because it is slightly counterintuitive. And so often we connect ln x and 1 over x in our brains that getting this into your head as the integral of ln x, I think, is worth the reinforcement. So I claim this is the antiderivative, which means when I take its derivative, I should just get ln of x. I'm going to leave off the plus c because the whole point of that is that it differentiates to 0. We know that the derivative, you can, plays nice with addition and subtraction. You can split this up and take the derivative of the first piece minus the derivative of the second piece. Now that first piece requires a product rule. And the product rule says that f times g primed is f prime times g plus f times g primed. So this piece I use the product rule on. My f is like the x, my g is like the ln of x. So f prime times g is 1 times ln of x plus f times g primed is x times 1 over x minus is this minus, and the derivative of x is 1. And finally, 1 times ln of x is ln of x. X times 1 over x is 1, and you've got the minus 1 at the end. 1 minus 1 is 0, so this is just ln of x. I won't lead you astray. This was a correct use of integration by parts up there. Okay, so indeed, the integral of 1 over x is ln of x, but the integral of ln x is x ln x minus x. Kind of weird. Kind of weird. I want to thank the folks who turned their cameras on. It really, I genuinely do appreciate that. It really helps me follow how you're feeling about the material. I just want to remind everybody else, if you can, turn them on, keep them on. If you can't, I understand, but I genuinely appreciate it. So thank you to those who can and have. We haven't done any examples of definite integrals by parts yet, right? I gave you 2 formulas at the start of class, one for indefinite integrals and one for definite integrals. What I would like to do now is get some practice with the second flavor, right? Item 2 there. I do have a separate proof for item 2. Like I said, it's not something that we're going to go through in detail here in class, but I do have it in your modules. If you scroll down, so there's a review material module with everything you need, including like a bunch of graphs you need to know, rules from Calc 1, trig review, all that good shit. If you come down here, Stack Exchange post on IBP, a better picture proof. Oh, here it is. I just didn't want to open in Canvas. This is a really nice way to think about what that formula is saying. This red curve is the function we're integrating. And we want to integrate from here to here, which would be from U1, whatever, 2-ish, to U2, which looks like it's about 10-ish. The integral we want is the integral of u dv taken from 2 to 10. So that's the light gray area. The total value of all the shaded area here, right, the gray shaded area, would be this height times this width minus this height times this width, which is u2 v2 minus u1 v1. Right, it's the big rectangle minus the blue rectangle. The light gray shaded area would be the integral from u1 to u2 of u dv. And the dark gray shaded area, if you turn your head sideways, could be thought of as the integral from v1 to v2 of v du. So I encourage you to go to the modules, scroll down to integration by parts, click that link, study this picture, and if you like, read some of the discussion here. It's a very nice discussion. Stack Exchange, BT-dubs, is a dope website for any and all things mathematics, programming, etc. Research mathematicians routinely post to Stack Exchange for help with their own things, and we are not better than them. We can definitely learn from that too. So a definite integral done by parts. Those who have taken classes with me before know that I have favorite functions. Now, every function is a dude, is a guy, and they have personalities. And one of my favorite functions is the inverse tangent function. He's a cool dude. I like him a lot. This, as a definite integral, has an interpretation in terms of areas. The graph of the inverse tangent function is a graph you should know. It is a graph I could ask you to draw on a test. It looks like this. It is an odd function. It is symmetric about the origin. Has two horizontal asymptotes, pi over 2 and negative pi over 2. This is the graph y equals inverse tangent of x. And what I'm asking you to do here is to find the area from 0 to 1, bounded by this function and the x-axis. Kind of like the natural log integral, this doesn't look like something you would differentiate using the product rule, right? You wouldn't. You know the derivative of arctan, and it doesn't require the product rule. But integrating it does require integration by parts. Again, thinking of your LIPET rule can be helpful guidance here, right? There's an L at the start of LIPET, so if there are logs in your integral, maybe IBP. The next thing is I. Well, this is an I function, right? This is an inverse function. It's the function that's defined to be the inverse of the tangent function. So we do set this up with IBP. And following LIPET, my choice for u, there are no logarithms here, but there is an inverse function, so I should choose that to be u. And dv has to be everything else. Again, that's just dx. Who remembers the derivative of the inverse tangent of x? Anybody help me with that? Yes, thank you, Queen King. So the derivative of this function, the derivative of arctan, is 1 over 1 plus x squared. So the differential du is 1 over 1 plus x squared dx. And since dv is dx, v is just x. So there's my little integration by parts table. And just remember that you're using the definite integral version of your integration by parts formula. So the integral from 0 to 1 of the inverse tangent of x dx is equal to u times v. And again, I'll write the x out front. So this is x times the inverse tangent of x minus the integral from 0 to 1 of v times du, which is x times 1 over 1 plus x squared dx. And I'm going to stop here and say, I've intentionally made a mistake that I want one of you to catch. What is the mistake here? Two bonus points on exam 1 to the first person who can tell me the mistake.
So you have to put x and then inverse tangent x from 0 to 1.
Very good. So that's Matthew. I'll make note of that. We need to evaluate the UV piece, right? This is the thing that people always forget. The definite integral version of the integration by parts formula requires evaluation brackets around this part. You have to evaluate everything from A to B, including this first piece. And if you write this line down without the evaluation here, even if you evaluate at the end, this line would be wrong. So that was Math J. Thank you. All right, now we're ready to proceed. We should do the evaluation here before we start crunching on this integral, because this is a lot to write. And these things usually they necessarily simplify to just a number. So let's find what this number is, and then we'll worry about that integral over there. When I plug in 1, I get 1 times the inverse tangent of 1. So this piece here is 1 times the inverse tangent of 1 minus 0 times the inverse tangent of 0. So this piece is going to be 0. Not worried about him. This piece is going to be just the inverse tangent of 1. What is that? What is the inverse tangent of 1? Very good. Pi over 4, right? It's the angle between negative pi over 2 and pi over 2, such that the tangent of that angle is 1. And there's only one such angle. It's pi over 4. So this is 1 times pi over 4 minus 0 times, while we're here, what's the inverse tangent of 0? I know it doesn't matter, but tangent of what angle between negative pi over 2 and pi over 2 is equal to 0? You can look at the graph above to help. That's the y value on the graph here at x equals 0. Yeah, very good. Okay. So this whole piece right here is pi over 4 minus 0. It's just pi over 4. Getting that out of the way, now you don't have to write it all the time. Now let's turn our attention to the integral. How do you do this integral? Good, it's a little substitution. I'm not going to use the letter u because the letter u has already been utilized over here in our integration by parts, and it can be confusing to label two things with the same variable. So we do a little substitution, and I'll use the letter z. Oops, sorry, z. The substitution we're going to make here is up here. Z equals the bottom, 1 plus x squared. dz then is 2x dx. The other thing we need to do is change our bounds, because I'm making a substitution in a definite integral. So when x is equal to 0, z is equal to 1. And when x is equal to 1, z is equal to 2. So this integral is going to become the integral from 1 to 2 of dz was 2x dx. So here's my x dx. That's going to get soaked up by dz. This says 1/2 dz is equal to x dx. There's going to be a 1/2. And then 1 over 1 plus x squared is 1 over z. So it's 1/2 times 1 over z dz. So altogether I have pi over 4 minus 1/2 times the integral from 1 to 2 of 1 over z dz. Integrating 1 over z gives me the natural log of z. So this is pi over 4 minus 1/2 times the natural log of the absolute value of z evaluated from 1 to 2. We use the new bounds. And I'll remind you on the test, I require you to change bounds when you make a substitution in a definite interval. Got to do it. And the beauty is you don't need to go back to the original variable. We just plug in these new numbers. Doing that, I get pi over 4 minus 1/2 times the natural log of the absolute value of 2, which is 2, minus the natural log of the absolute value of 1, which is 1. And there's one final thing to do here. And that is to tell me what this is. What is the natural log of 1? Very good, it's 0. So the integral from 0 to 1 of the inverse tangent of x is pi over 4 minus 1/2 times the natural log of 2. Okay. No noise. We're not yet done with integration by parts. There is one more family of integrals that we need to talk about that we haven't spoken about yet. I think I did put some of those problems in your homework set for this week, so I'm going to have to go in and pull those out. Now I'll do that for you. We'll talk about these remaining integration by parts stuff next time. Maybe what I'll do, I'll just extend the homework so that it's not due on Monday of next week, but like Wednesday of next week. Just so that those who want to see it can see it. Very briefly, I'm going to describe the problems I'm talking about. I'm not going to do them or push this lecture any deeper past being where it should. These are called looping integrals. And if you go onto my YouTube channel, if you want to do this stuff early, you can see there. I have in the Calc 2 playlists plenty of videos on looping integrals. These are things like e to the ax times cosine of bx, or e to the ax times the sine of bx, where a and b are constants. These are quite strange problems in that we don't solve them directly, but we do integration by parts twice, and the original integral shows up again. So what you get is like you get like your integral equals a bunch of stuff minus some constant times my integral. This is what you'll have after 2 runs of integration by parts on either of these. And you can choose U and dv using LIPET still. And the way you solve this is by adding this thing back over. So then you'll have some new constant, right? My integral plus some constant times my integral. You'll have a new constant times my integral equals this bunch of stuff. And then you just divide by the constant. That'll get you my integral alone. These feel very weird the first time you see them. So I don't want to rush them and force them into today's lecture. I want you to have a chance to play around with integration by parts and work the homework problems a little bit. I think there's just one problem like this in your homework set. So what I'll do, maybe the move is to pull that problem out. Yeah, from your homework, I'll pull that problem out and I'll put it into next week's homework. That way, you need to, by Monday, finish all the other integration by parts stuff. And then on Monday of next week, I'll run through an example like these, and then we'll move on to the 7.2 material. There are many videos online. There are videos posted in the modules section. If you want to take a look at examples of these problems, you can. But between now and Monday, make your focus just finishing up the other problems in the WebAssign homework. I suppose it's possible that somebody has already done that. Maybe I should just extend it. But I really want you to finish the other ones. You guys are grown-ups, right? So if I extend the homework set just so you have some time to work this problem on Monday, you know that that doesn't mean you should wait to do all the other stuff, right? Do all the other stuff. Just save this problem until next week. That's what we'll do, because some of you have probably already done it, and I don't want to take those points away from you. So that's it from me for today, guys. If you do want to talk to me, I have an office hour today from 1 to 2 p.m. You can always send me Canvas messages, or on the Discord, you can get a hold of me. Yeah, so like this is an algebra equation, right? Like if I had x equals some stuff minus 2x, you would add 2x to both sides, and then you get 3x equals a bunch of stuff. That's the game. Yeah, it's pretty neat. So the 2 runs of IBP turn this integral into an algebra problem, and then you solve the algebra problem. It's a very clever move. And you'll see similar things in differential equations with the Laplace transform. But that's it for me for today. I've already taken up enough of your time. I'll let you guys go. If you want to talk to me, Canvas messages, emails, Discord, and office hours. Office hour begins in 20 minutes. So that's the best thing if you need it. Otherwise, I will see you on Monday. Please finish up all of the integration by parts stuff except for this one, right? Everything else you want to have done by Monday, because there will be a new big homework set on Monday of next week. You don't want to be behind. So I will extend that so that you don't need to worry about doing this before Monday, because we haven't done it in class yet. If you want to do it, go ahead. Otherwise, save just that one for Monday. Do everything else. On Monday, we'll begin by talking about looping integrals, and then we'll move into talking about integrals of trig functions. So take care, guys, and I'll see you next week.